Hello, everybody. I'd like to welcome you all again to this month's EarthShift Global's Brown Bag webinar. And today we're very happy to have Timothy Scone with us, who is a senior environmental engineer within the Department of Energy, National Energy Technologies Laboratory Systems Engineering and Analysis Directorate. He leads life cycle analysis research efforts within the Office of Fossil Energy on Carbon Utilization Technologies, methane emissions from the natural gas value chain, alternative transportation fuels, advanced power generation systems, and energy water impacts. Mr. Scone is an elected member of the Society of Environmental Toxicology and Chemistry, CTAC, of the North American Life Cycle Analysis Interest Group, CTAC liaison to the American Center for Life Cycle Analysis, member of the University of Michigan Global CO2 Initiative Advisory Board, and founding organizing member of the Federal LCA Commons. Mr. Scone has over 21 years of experience in the field of energy analysis and is a graduate of the Penn State University. So without further ado, I will let him take over, and welcome, Tim.
Thank you, Holly, and thank you, everyone. I'm looking forward to a good conversation today. I want to start with talking a little bit about water and decarbonization and the importance of water in society to kind of set a bit of a stage. Our colleagues at the U.S. Geological Survey put together this infographic, and it really kind of begins to depict and really sends the message about really how precious water is on the planet Earth. Now, most of you like me who grew up looking at the globes and the atlases, or even been to the beach or one of the Great Lakes looking out over, and it looks like an endless body of water. There's so much blue on the maps and the globes. When you sit at the beach and look out, all you see is water from that perspective. And it makes you think that the planet is rich in water. But the question is, are we rich in water that supports human life? And that's what we care most about. So here in this infographic, the size of the globe represents the total volume of the Earth. The large blue dot over the western part of the United States actually represents the total amount of water in relation to the land mass of the planet that there actually is on the planet Earth. Because most of that ocean water is only surface level deep from that perspective. The medium-sized blue dot over the Kentucky gives you the perspective of how much fresh water is available on the planet. And that very small blue dot around Atlanta, Georgia, that's actually how much fresh water is available from lakes and rivers to sustain human life. Of all of the water on the entire planet, only about 0.007% of the Earth's water resources are suitable for supporting human life. So that concept of the Earth is 2/3 water, and when we sit at the beach and we look out the endless body of water, that is not the reality of how precious our water resources are to support human life and other life forms on the planet. And so as we think about our strategies towards decarbonization, today I want to expand your thinking a bit about the impacts of other environmental categories, and particularly the stress that we put on freshwater resources. So this is not a new topic by any stretch. Our colleagues around the globe at the United Nations Environmental Program have identified water as a fundamental to life on our planet, but this precious resource is increasingly in demand and under threat. Within their framework, they've established sustainable development goals, and goal number 6 is around clean water and sanitation. Several of those sub-goals, 6.4, 0.5, and 0.6, all relate to the need to conserve and effectively manage our water resources, particularly around thermoelectric power generation today. Now, our colleagues here in the United States at the U.S. Environmental Protection Agency have said that while climate change is changing our assumptions about water resources, as climate change warms the atmosphere, altering our hydrologic cycle, changes to the amount, timing, form, and intensity of participation will continue. So clearly recognizing not only is it the precious resource, but it's changing. The demands and the supplies are always constantly changing. And with climate change, it's going to only put further stress on our precious water resources. Today, I would like to talk to you a little bit about the role of water in electricity production, particularly thermoelectric electricity production, the life cycle water intensity from various forms of power production, some strategies around decarbonizing thermoelectric power generation, comparing and contrasting water intensity of thermoelectric power generation in a decarbonized future, and some concluding remarks and opportunities. I would like to set the stage that the goal today is to expand your thinking around environmental impacts. While clearly important and the intensity of the spotlight of climate change on research today and on the direction of the administration and the direction of nations around the globe, it is important to recognize that there are other environmental impacts. There are trade-offs potentially and potentially advantages. And we need to recognize those trade-offs and advantages so that we can effectively mitigate them to have solid and sound and sustainable solutions. And so life cycle analysis is a framework that we use here at the Department of Energy and the National Energy Technology Lab to help assess these differences from both a pathway, portfolio, or technology level. So let's start with a little bit about the role of water in electricity production. Once again, our colleagues at the U.S. Geologic Survey back in 2015 did an assessment on water withdrawal from a national perspective. Now, water withdrawal is the amount removed from an existing water body. And so from that perspective, you can see on the graph on the right that thermoelectric power is about 41% of that total, and about 34% of that is coming from our freshwater resources. So to give you perspective, it's about 133 billion gallons per day of fresh water is withdrawn from our resources to support thermoelectric power generation. And so this is a critical asset in order to maintain our thermoelectric fleet and to be able to provide that power that's necessary to drive our economy. But we need to take these into context with our water requirements. Well, this is about water withdrawal and how much was removed. We also need to think about it from the perspective of water consumption. So how much of that water is actually lost during the thermoelectric process through one route or another that is no longer available to be returned to a water body for additional use in the future. So unfortunately, USGS was not able to update that study in 2015. And the current perspective goes back to 1998, when they did an assessment to try to understand freshwater consumption from that perspective. And so we've done some work as well to estimate that total. And here we see that it's about 3% of the total freshwater, or about 4 billion gallons per day in 2015. And I should say some recent work we've done sets that at about 2.6 billion gallons per day in 2018. And the reason for that is just decreases in thermoelectric power generation itself, as well as shifts between once through to recirculating cooling tower perspectives. So how is water really used in a power plant? Well, for those that aren't familiar, water is heated in the boiler to produce steam that then turns a turbine and a generator to produce electricity. After the electricity generation, the steam is then condensed using a separate cooling water stream. That cooling water stream is either directly discharged back to the source body of water, and that's referred to as once-through cooling, or it's recycled to lower the water temperature to improve heat transfer. That recycling typically uses a technology called a recirculating cooling tower. In the graphic to the right of the simplified thermoelectric power plant, I'm showing a cooling tower on the left in red. And so some of the sources that in that diagram you can see for the water losses, primarily being evaporation and drift from the cooling tower. We do have some blow down water, and we have some other losses throughout the system. But the key to this is understanding these flows, and that water is a critical asset in order to maintain the efficiency of our thermoelectric fleet. So another perspective on how that water is used. I introduced the concepts of once-through cooling, recirculating cooling towers, and now I'd like to introduce the concept of dry cooling. So dry cooling uses fans to move air over a heat exchanger to cool the water in a closed loop system. Fan operation increases that parasitic load and operating costs of the plant, but it decreases plant efficiency as a trade-off to conserve regional water resources. So the table here kind of gives you that perspective of the balance. If you're in a very water-rich area, where water withdrawal along a river for your power plant was once commonly acceptable in practice, but the trend has been moving towards more of the recirculating cooling towers so that that water can be available for downstream uses. Now, from a water management cost perspective, cooling towers would be the lower cost option, while recirculating cooling towers come with an increase in capital equipment and management. But dry cooling is significantly more expensive. But we typically see dry cooling now in the western part of the United States in more arid regions where water is a premium. But it does come at an additional capital expense, as well as a loss in the overall plant's efficiency. Now, I was talking about some of those losses across the power plant. On the right is kind of a Sankey diagram where we're showing the total water withdrawn by the source that it's needed to support a supercritical PC plant. And on the right side, you see the consumption values there. To give you perspective, I talked about the cooling water and evaporation and drift, which is a key component of that water loss. We have a little bit going out the stack with the flue gas, a little bit goes with the gypsum, which is some moisture, and then we have some blowdown discharge as well, which in that case is not a direct loss. Now that blowdown, though, we cannot send that to the existing water body. So that does need to get treated before discharge. So how has this been changing over time? So just to give you a quick perspective, between 1950 and 2016, which is the timeline at the bottom of this chart, you can see once through cooling technology in the blue line. In the orange line is the recirculating cooling towers. And then the red line introduces the dry cooling. And then there are some hybrid concepts that have come online. So you can see the decline in the once through cooling, and you can see the ramp up in the recirculating cooling towers, and a strong build in the early 2000s when a lot of the NGCC units were built around the country. And then you can see also the dry cooling coming in throughout. So we do have a mix, and there are various ages within the thermoelectric fleet today. So let's move forward a little bit, and I want to set a stage for you as I'm building the foundation here for a little bit on the life cycle water intensity of electricity production. So on the left-hand side, I've given some broad categories of the fleet level type perspectives of electric power generation in the United States. Now these values represent 2018 power generation, and the results in the graph are specific on a per megawatt hour basis. Now, for convenience, I have shown next to the labels in the percentage that it contributed to overall power generation in 2018. If you wanted to create a national mix from this, you would have to multiply the numbers in the graph by the percentages to create that percentage. We also have a tool that does that for you. On the left is water consumption, and on the right is the global warming potential on a 100-year time frame using the IPCC AR5 values. We do use it with climate carbon feedback. So our value for methane is 36 that we use in our work here. These results are the same thing, are also on a per megawatt hour basis, individual to the technology or fleet, and then the percentages that they contribute as well as shown there. You can quickly see differences here between water intensity and greenhouse gas intensity as you look from the left to the right on the different technology platforms for power generation. We're going to use some of these values, and we're going to move forward exploring a little bit more in specific technologies as opposed to fleet perspective, and kind of think about how these two come together in the future. So when we think about decarbonization strategies in the thermoelectric power generation fleet, there are a lot of them, and today I'm only going to talk about a small handful. I want to talk a little bit about carbon capture, utilization, and storage. I'll talk a little bit about adding biomass and co-firing, and what that can do for decarbonization using a biogenic source. And then we'll look at some advanced conversion technologies like fuel cells and hydrogen to power. Now, clearly, this list is not meant to be exhaustive of all the reduction opportunities for carbon reduction in the thermoelectric power generation fleet. Today, I just wanted to introduce the concepts about some of those trade-offs to expand your thinking about beyond just greenhouse gases to water intensity, as we think about the nuances in these evaluations and our strategies. So let's move forward and talk a little about carbon capture, utilization, and storage. For those that are not familiar with that concept, it's when we add post-combustion systems that remove the carbon dioxide from the combustion flue gas and then make it available for alternative use and storage. This essentially prevents the release of carbon dioxide to the atmosphere as long as it's not released once it's captured. Additional water is needed for the increased parasitic load on the power plant to operate the carbon capture and compression systems. So I want to take a moment, orient you to the graph here on the right side of your screen. And we're going to be using the similar setup for a few slides here and looking at the different technologies. On the y-axis is the water consumption. That would be the vertical axis. And so that's in liters per megawatt hour. On the x-axis, or the horizontal axis on the bottom, is the global warming potential in kilograms of CO2 equivalents per megawatt hour. The bottom left corner is the 0 mark on each of these. In each of these diagrams, there will be black colored dots and orange colored dots. The black dots represent the baseline or comparison technology that we're for this particular graph, and where the orange dots are going to reflect the with carbon capture in this case, or with biomass or with advanced scenarios. So the first thing that we want to recognize, and if we look at a supercritical PC plant, is that if we add carbon capture and storage to that, and in this example, I'm using geologic storage in a saline aquifer, you can see a significant reduction in the greenhouse gas emission intensity. We're moving from about 800 to a little below 200 kilograms of CO2 equivalents per megawatt hour of power. But we also see that the water intensity has increased. It's gone from about 2,000 liters to a little under 3,000 liters from that perspective, something that we need to be aware of and develop effective mitigation strategies for. So here we can see the trade-offs around decarbonization, and clearly a push of the current administration and globally is the deployment of large-scale carbon capture and geologic storage in order to meet future goals. Let's move forward a little bit and talk about biomass co-firing, once again with bituminous coal. So I'm going to keep that same supercritical PC plant. You can see that in the lower right-hand corner of the graph from that perspective. And so here, if you look above that dot and moving forward, we look at adding 20% by weight biomass, 35% by weight biomass as the feedstock, the other percentage is coal, and then 49% weight by biomass. And here we're using a dedicated short rotation woody crop as our biomass source. So here we can see decreases in the greenhouse gas intensity associated with that. Now, when we combine that biomass input with carbon capture, now we have the potential of capturing not only the fossil, but the biogenic carbon emissions. And when we sequester those biogenic carbon emissions, we have the opportunity to potentially get negative emissions technology. And of course, that depends on everything else in the life cycle and their contributions, as well as the amount of biomass put into the system. Here, we're able to balance the economics and the environmental perspective between using biomass for better green climate change performance while using the coal to maintain a lower overall cost of power delivered. We can even see here with 35% and 49% weight biomass with carbon capture, we are at net zero or below from a power intensity perspective, something that will be critical to helping meet our future goals. Let's move forward a little bit and talk about advanced conversion technologies. And I just picked two, fuel cells and hydrogen to power, right? And so this is, keep in mind, hydrogen to power. So we're going to reform or produce hydrogen, and then we are going to combust that hydrogen to produce electricity. So the solid oxide fuel cell produces electricity by a chemical reaction instead of combustion. Recirculating cooling towers are still used for heat transfer and are the primary source of water consumption. For hydrogen production and combustion, both consume water. Hydrogen production by electrolysis also requires water as a material input, in addition to cooling and combustion gases. So that's an important thing. Most of the conversation I've had today is around using water as a cooling mechanism for these operations. When it comes to hydrogen production with electrolysis and using energy from electrolysis, we also have water as an input to that process. So here I did change the basis of the comparison point. Since we are looking at advanced conversion technologies, I changed that to a natural gas combined cycle with CCS is now represented as the baseline technology. And so here you could see solid oxide fuel cell options. You could see the hydrogen, PEM electrolysis or polymer electrolyte membrane powered by a wind farm from that perspective. And then and in this case, in the upper right-hand corner, we have hydrogen and coal gasification with CCS and hydrogen steam methane reforming with CCS. And so in this case, showing that if you're going to go from natural gas to hydrogen to power, you're having an amount of significant efficiency losses. In this case, you're better off going natural gas direct to power and resulting in a better environmental performance. But these are the types of things that we need to understand when we think about the trade-offs between decarbonization and water intensity. So this one just puts all of that data into one chart to make it a little bit easier as a reference for looking at. And as we kind of think about our strategies from a policy perspective and our strategies from a technology development perspective, we really want to understand this greenhouse gas reduction and the water conservation aspects for thermoelectric power generation. These are both critical to our designs and our strategies going forward. Now, while today I'm focused on greenhouse gases and water intensity, these are not the only environmental attributes that of interest to be of concern. So a full spectrum life cycle analysis with full impact assessment will really provide that full spectrum for you, from different air emissions, non-GHG air emissions, direct emissions to water, and things of like. So, some concluding remarks and some opportunities. So the first one I want to mention is that the future is really uncertain. That the growing demand for energy, though, is certain. And that we do know. Every projection around the globe from every institute has predicted that global energy demand will increase. Decarbonizing our economy is a priority today. And it is clearly a strong priority within the Department of Energy and here at my lab, at the National Energy Technology Lab, as we work to move forward towards a decarbonized society. Decarbonizing thermoelectric power is going to be a priority. As we think about our future, and we think about even just decarbonizing the transportation sector with the electrification of vehicles, for example, that's still going to put an increased requirement on the demand for electric load as we shift from transport to the power sector. Even in there, we need to ensure that we can effectively drive those economies forward. And we need to make sure that the thermoelectric power supporting our economy meets our decarbonization goals and environmental stewardship. Decarbonizing thermoelectric power does increase water intensity. We've seen that today in most of the trade-offs I've presented. Low carbon strategies call for a reduction in fossil-based thermoelectric power without carbon management. And that's critical, without carbon management. I hear a lot of discussions today of a push to reduce fossil fuels. And my argument is absolutely we need to reduce high greenhouse gas intensive power generation. What we need to do is provide environmentally sustainable power generation solutions. And some of that may be with fossil fuels, with effective carbon management and biomass, and other hybrid synergies with renewables to balance that perspective and meet our objectives. The economic and life cycle environmental performance will drive technology change to meet future priorities. And this has been demonstrated time over time. And I will say that the life cycle environmental performance is something that I am proud to see really growing in society and around the globe today. To even the inclusion in key companies, CEOs, compensation packages these days include requirements about greenhouse gas or environmental performance. This has become part of our culture and is here to stay. And LCA is going to be one of those tools to really help inform and drive that forward. And the sustainable water practice remain a priority today and into our future. All right, so some challenges and opportunities to leave you with. So challenges really meeting this growing energy demands. We are working on significant, massive reductions in decarbonization goals, but yet we have growing energy demands, and we need to put it on a scale unlike anything we've done here in the country around the globe before. And so we have some real challenges and some real scientific hurdles to overcome, but I am confident that we will find paths to overcome these challenges and meet our objectives. But we need to ensure that the solutions are balanced effectively. We need significantly reducing greenhouse gas emissions and sustainably managing water resources to support life. And that last part is critical. A lot of the solutions I hear are talking about really increasing that water intensity as we saw today. And so we need to understand these at the regional level, We need to understand where they can be effectively deployed and which areas would be high risk and we would cause more stress with those types of solutions. And we would need alternative solutions for those areas. So some opportunities for water reduction. Existing power plant water reduction strategies are going to be critical. Dry cooling cost reduction and performance improvements to make switches into that direction, which would eliminate the water. Alternative water use. I talked a lot about fresh water use today. What I really didn't bring into the discussion with me was about that of alternative water use. There is opportunities for the synergies of cleaning and preparing alternative or impaired water today for use for cooling plants. That would reduce the need for fresh water in that perspective. Hybrid thermoelectric and renewable power plant concepts. And then, of course, innovation. And innovation is the key, I think, to these opportunities. And that's whether it's around demand reduction or regional water scarcity alignment, combinations with hydrogen and renewables and fossils. We need to ensure that we can meet the needs of our society while protecting our water resources and our climate and other sensitive environmental areas, so that in balancing these sustainably. These are key drivers today and things that I know as a group, we will continue to work towards effective solutions that are necessary to meet our goals. With that, I'd just like to conclude by saying thank you very much for your time, your attention, and your interest in this topic. If you are interested in accessing any of the resources on a life cycle analysis perspective, produced by the National Energy Technology Laboratory. The links here at the bottom will take you directly to our area. So netl.doe.gov/LCA will take you to the website where we post all of our presentations, reports, models, and tools. If you have a direct question on one of our products or would like to ask us a question about something, we have a direct email box at lca@netl.doe.gov. And with that, I think I'm going to turn it over to Holly and see if there are any questions today that people would like to discuss.
Oh, great, Tim. Thank you for a very interesting presentation here. And we do have some questions. The first person says, really interesting, Tim. Looking at the supercritical scenarios, the graphs show water consumption. Have you considered these from a water scarcity perspective?
So in the results I showed today, I did not overlay a regional water scarcity aspect to it. And so those are what I would consider attributional profiles for the technical performance of that operation, given the particular, in this case, the bituminous coal supply combined with the supercritical PC plant. Now, there's been lots of great work done by Argonne National Labs and NETL using a tool called AWARE, which was developed out of the UNEP originally at a global level, but Argonne National Lab has moved that forward and created a North American version. And it really is focused at looking at that water scarcity, where we are combining what the water withdrawals and demands are from other sectors, along with the thermoelectric sector, and then understanding what the water resource availability is. The tools that we worked with our colleagues at Argonne National Labs with the AWARE model really does that at a seasonal level, so it gives you a monthly perspective as well as an annual perspective. And so when we think about water scarcity and regional aspects, we take these types of results that I'm showing you today at a high level and bring those into a true water scarcity model at the regional side. Great question.
Okay, thank you. And with the current administration goals to decarbonize the electricity sector by 2035, will we still need coal and natural gas thermoelectric power?
Great question. I touched a little bit about that on my talk, and let me expand upon that. And the short answer is absolutely yes. In order to maintain and meet the electricity energy demands, particularly in a future decarbonizing scenario, all projections have shown that we are going to need a reliance on some form of fossil energy until we're able to grow out new innovative strategies around hydrogen combinations with renewables and others. Right now at a global level, it's critical that we find ways to decarbonize that power and manage the other environmental attributes. And all of the long-term strategies that you will see out even to 2050 all include some level of fossil fuels to provide base level support. And so it is decreasing, and we clearly recognize that in that strategy, and we are supportive of an all above strategy. We just want to make sure that we can still provide the electricity and keep the lights on while we march towards these objectives. Great question.
Thank you. Reducing carbon emission with carbon capture technology demonstrates a trade-off in environmental priorities. How is the Department of Energy addressing this competing challenges?
Another great question. So here at NETL, we have several programs focused in this area. We have a water program that is specifically focused on the energy-water nexus around this topic. We have a carbon capture program, and the water intensity and demands that it increases associated with including that carbon capture technology have been a core thrust for years in our program as we look to identify those. More recently, the Department of Energy has stood up the National Alliance for Water and Innovation, NAWI Hub. So this is a collective of external and internal DOE organizations, all focused on minimizing water requirements for thermoelectric power for future energy demands. I'm happy to provide some links on those different initiatives, both within NETL and the broader DOE for those that are interested. Thank you.
Thank you. You identified a few challenges and opportunities for water reduction in the future, but what do you see as the greatest opportunity?
Great question. So the things I see as the greatest opportunity is the innovation. We need to find those solutions that can balance both the economic, the environmental, and the social aspects to meet society's needs here and around the globe. And so I do see renewable power generation growing. I see hydrogen clearly in time will come in to help replace some of the fossil resources as we grow out those renewables. But make no mistake, I still continue to see a strong backbone in the fossil power with carbon capture, whether that's the storage or utilization, to further decarbonize and balance that perspective. And so I'm excited to see what the researchers have yet to come up with for solutions. And every couple of years, I am surprised by something that comes along and some great innovation. And I am excited about the breakthroughs that we have yet to envision.
Well, I'm certainly glad you're so optimistic. That's wonderful. Are water consumption and other water impacts well understood in the LCA field?
That's a bit of a yes-no answer. In general, I like to say no, in the sense that water often gets the treatment of it's that other thing we pick up along the way, unless someone has specifically asked or directed that they want to have a focus on water. Now, that isn't to say that the LCA community ignores water at all. There has been an ISO standard developed around water footprinting that really sets a foundation and guidelines around this process. The work we've done, specific water footprinting here at NETL, as you can see, where we take a strong focus, and others around the community have also taken strong focuses on trying to better characterize and understand our water resources. Now, but in the big picture of things, greenhouse gas and criteria air pollutants are well managed, understood, and reported from different government perspectives, where water consumption has a much lower threshold and much lower volume of data collected that makes it available for us to analyze and understand and therefore create effective strategies. So that's a bit of a yes-no answer, and I encourage everyone to continue to expand and push to your impact assessment categories with folks to say that really the goal here is, with LCA, is to make sure that not only are we shifting burdens up and down our supply chain, but that we're not shifting burdens from one media to the other. When you focus only on greenhouse gas emissions or criteria air pollutants, you're missing large portions of the puzzle, and that would be the water and land aspects. So we like to see all of those in a balanced perspective to help inform decision makers on effective environmental and sustainable strategies. Great question.
Somebody else says, does the water vapor from the thermoelectric process enhance the greenhouse effect?
A good question. So in the debate around greenhouse gas emissions, the IPCC, which is the International Panel on Climate Change, does recognize that water vapor is a contribution that does have an effect around on our radiative forcing or climate change. However, it is also considered to be dominated by the evaporation from oceans and the larger Earth systems. And so the contributions directly from thermoelectric power plant and any other source are currently excluded or not strongly considered. So you won't find a global warming potential value like you see for methane or nitrous oxide or hydrofluorocarbons for water vapor. And so while the water vapor contribution is not accounted for and any impact associated with that from a climate change. But there is a lot of science and discussion going on in that space. And I encourage anybody that has that interest, there's great discussions in the science section in the IPCC's assessment reports.
Thank you. I have room for one more question here. And how can I learn more about LCA modeling and analysis conducted at the U.S. Department of Energy National Energy Technology Laboratory?
One of my favorite questions, and the slide up on the screen is a great indicator to that. The first place I would always recommend folks to go is to the LCA website here at NETL. And that's at the link of netl.doe.gov/LCA. And from there, you will find things broken into different technology categories, from coal to biomass to natural gas, liquefied natural gas to petroleum to other categories, including renewables as well, as we cover the full spectrum from that. There is a unit process library there that you can download individual unit processes that we've developed and used in our work to support our analysis, as well as more simplified models and tools. So at the bottom of the page, you'll find links for presentations, models, tools, unit process library, and that'll all help guide you in that direction. If you have any particular questions or are looking for something specific, feel free to email us at lca@netl.doe.gov. Now, I will tell you, we don't have every resource, but the things that we do have, we are happy to point people in that direction from that perspective. Thank you.
Well, thank you so much, Tim. This was quite interesting and informative. I want to thank you all for coming, and I will end this webinar. Thank you. Bye now.